Hi, so today we're doing problem 313, and 313 just says that we should find the potential in the infinite slot of example 3.3 if the boundary at x consists of two metal strips, one from 0 to y is equal to a over 2, is held constant at a positive potential v0, and the other goes from a over 2 to y at a negative potential negative v0. And that looks like this. So, same exact boundaries as example 3.3, except now we have a negative v0 above a over 2 and a positive v0 from 0 to a over 2. And I actually already drew this, kind of like this, as you can see. So, to start off this separation of variables problem, I'm going to start out with the general solution, write out my boundary conditions, apply my boundary conditions, and then we'll keep simplifying from there. So let's get started. So if you read Griffiths, it says that the general solution for Cartesian coordinates of a separation of variables problem is that potential for x, y, and because we are finding the potential within the slot, z is not a variable here, is x as a function of x, y, y. And it looks like this. And this easily gets simplified to a e to the kx plus b e to the negative kx. And c sine ky plus d cosine ky. So here, this is just our x, here, this is our y. And that's our general form. So I'm going to start writing out the boundary conditions. Boundary condition 1 says that for y is equal to 0, potential is also equal to 0. Boundary condition 2 says that for y is equal to a, potential is equal to 0. Boundary condition 3 says that as x goes to infinity, as we go along the x-axis, potential is also equal to 0. The fourth boundary condition is a piecewise condition, which says that for 0, y between a over 2, potential is equal to a positive v0. And when a over 2, y is between a over 2 and a, potential is equal to a negative v0. So we're going to apply these four boundary conditions to our general form and simplify even further. So boundary condition 1, applying that, says that for v x 0, because y is equal to 0, we get a 0 potential. So we can just write this as its general form for now, because we're just dealing with the y's. And this is a c sine k 0 plus d cosine k 0. Put that all in parentheses, and this has to equal 0. So, looking at this, we can see right away that sine, this form just goes to 0. This is just left. Cosine k0 is just equal to 1. So, this becomes d is equal to 0. Boundary condition 2 says that for v, when y is equal to a, we're going to plug in a for y, so c sine k a plus, since d, we already said that d is equal to 0, we can just write 0 here. And this whole expression is equal to 0. So when is this term, so when is c sine ka equal to 0? Well, c sine ka is equal to 0 when ka is equal to n pi, because for n pi, sine is equal to 0. So solving for k, we get k is equal to n pi over a. Okay, so 2 boundary conditions down, 2 to go. Applying third boundary condition, we see that as x goes to infinity, potential goes to 0. So we're going to do v, we're going to plug in infinity for x, and then y just gets left as y. And see, now that we're working with the x condition, we can just write that as yy. So for a, e, k to infinity plus b, e to the negative k to infinity of y is equal to 0. So we can see immediately that this form just blows up. It just gets really big. But this form actually just goes to 0. So for this boundary condition to be true, just like in boundary condition 1, a would have to equal to 0, because we already solved for our k, and this is blowing up so for this to be true, a has to equal to 0. So okay. We now need to apply our fourth boundary condition, but before we do that, I want to do a little bit of simplification just to see what we have so far. So far, for the boundary conditions we have applied, v of xy is equal to, so a is 0, and we get b, e, k is n pi over a, so we have negative n pi x over a, and times c sine k, so n pi, this time y, right, y over a, and we said our d and a are equal to 0. So this is what we have so far. What we can do is absorb b into c so that we have c e to the negative n pi x over a sine n pi y over a. So this is what we have so far. Now we can apply our fourth boundary condition. So all we did was applied 3 boundary conditions and then did a little bit of simplifications with our findings from applying the boundary conditions, and now we have this. So let's apply our fourth boundary condition. Our fourth boundary condition says that v is equal to positive v naught when y is between 0 and a over 2, v potential is equal to a negative v naught when y is equal or between a over 2 and a. So what we can do is say that at this boundary when x equals 0, we get a piecewise. So I'm going to write that out. So v when x equals 0, right, for y is equal to, so this is going to be 0, c e to 0, that'll go to 1, sine n pi y divided by a is going to equal to this piecewise, where y is between 2, potential is equal to positive V naught. And then when y is between a over 2 and a, potential is equal to negative V naught. So in order to solve this, we're going to apply the Fourier trick to both sides of this equation. So I'm going to write this in a way that makes a little bit more sense, and then I'll apply the Fourier trick. So C, and this is n for some n, because it's a coefficient. So Cn sine n pi y over a, speed this up so equal. It's equal to V0 y. And what I'm going to do is apply the Fourier trick. So this is what we have so far. And applying the Fourier trick, we integrate from 0 to a Cn, right? This is just what we've had so far. And we're going to apply the Fourier trick by taking the integral and also multiplying both sides by n prime of the sine. And this will look like this. 0 to a v 0 y sine n prime. Oh, there's dy that goes in here. N prime by y divided by a dy. When you do this, you can apply the piecewise, and we'll get two separating integrals. But first, this side, the Fourier trick says for when n is equal to n prime, Cn gets pulled out. And this says that for the Fourier trick, sine n prime dy, this will just equal to a over 2. So as you can see, we have that for dy, and this will just be a over 2. So now we want to apply our piecewise. So from 0 to a over 2, we get a positive V naught, sine, and we also want to say that n is equal to n prime. So we can actually write this as just n pi y over a dy minus, right, because minus, we're just pulling out the negative sign, a over 2 to a v naught sine n pi y divided by a dy. So now I can continue solving for this. I'll just leave this on this side for now, and then we'll solve for both these integrals. Solving for both these integrals, we get v naught. Sine goes to a negative cosine, so this is going to be, just pull out a negative 1. Do the antiderivative of that, and we'll get an a, right, over n pi, and this will be cosine n pi y divided by a over 2 to 0. Like that. That's just for the first part. And then for this part, we'll get a negative, pull out the v naught again. We'll also get a negative 1, a, n pi, cosine n pi y over a from a to a over 2. And we'll go like that. Okay, So from here on out, I'm just going to keep doing some more algebra, keep simplifying. I'm missing an a over 2 over here. So yeah, we'll keep going. Looks like we can pull this all out. That'll make it all nice. That way we can write it as v naught a over n pi. I'll also I'll leave the negative sign here for this one. So it'll be -1. We'll put this in a big square bracket. Cosine a over 2, so it's n pi over 2. Yep, that looks right. Minus cosine of 0, and that'll just be 1. And we'll put that in brackets. This can just be turned into a plus, and we already pulled that out. So this will just be cosine a, so we just get n pi minus cosine pi over 2 to y n pi over 2 again. Then square brackets. And then from there, we can simplify even more as we keep going. So Cn a over 2 is equal to v naught a n pi. This will be negative cosine n pi over 2 negative plus 1, nice, plus cosine n pi minus cosine n pi over 2. So from here, these two terms combine. We got plenty of paper here, actually, so we can keep going. So these two terms combine. This, actually, you can send as cosine n pi. It's actually equivalent to -1 to the nth power. So this will be Cn a over 2 is equal to v naught a over n pi 1 plus -1 to the nth power minus 2 cosine n pi over 2. We can go even further. That way we can actually evaluate what Cn really is. This is like a really general form. But for now, we can actually move the a over 2. That way our Cn is equal to 2 v naught n pi, right? The a, these cancel. 1 plus -1 to the nth minus 2 cosine n pi over 2. So we're almost done. So from here on out, I'm going to use a calculator to help us solve, and then we're just going to find out what coefficients of C1 actually are. So I did a calculation for anything inside the square brackets, and I applied when n equals 1, inside the square brackets is equal to 0, when n is equal to 2, inside the square brackets is equal to 4, as you can see I've done on my calculator. And the pattern I've noticed is that odd numbers go to 0, And even numbers not divisible by 4 go to 4. So 2, 6. But you can see that 4, when n equals 4, goes to 0, and equals 8 goes to 0. So really, we can write our final solution after applying all of our boundary conditions as v x y is equal to 8 v naught over pi is the summation when n equals 2, 6, not 8, 10, not 12, 14, is equal to e to the negative n pi x divided by a sine n pi y divided by a all over n. And that is our final solution. Thank you for watching.